Hi guys, welcome back to the next lecture of the crash course of strength of materials. In the last lecture, lecture 1.2, in the introduction part, we have concluded our discussion by elaborating on what kind of effects or end results we will get due to application of couple on different axes, say transverse axis or longitudinal axis. If it was couple is applied about longitudinal axis, it will be a case of torsion. If it is applied about transverse axis, any one of the transverse axis, it will be a case of bending moment. So that's what we discussed in the last lecture, and we have said that we are concluding the chapter 1 with that lecture itself. But the case is no, there are few more important things that we need to discuss prior to the entry into the actual subject. That is must for us. There has to be some bridging between the material science concepts and the strength of materials concepts, with certain definitions and things to be elaborated before entering the actual subject. So I am incorporating two more lectures, lecture 1.3 and lecture 1.4, before we get into the actual subject. So this lecture 1.3, we will be discussing this stress strain graph, things about stress strain graph and few other things. Now before telling you anything about stress and strain things, let me tell you start it with one small example. Suppose you are there and some person is trying to push you, right? When somebody is trying to push you to avoid falling down, you will resist the applied force or applied load. Similarly, any material will also resist the externally applied load. How it will resist is, it will develop some internal force which will resist the external force, and the internal force will be distributed across certain area which we will call as restricting or resisting area. Now that resisting area, resisting force developed divided by resisting area will is stress generated in the body due to the load applied. This is resistive force Fr, this is resisting area Fa, AR, Fr and AR. So that will be the stress. Now when such thing happens, stress is generated, that is force is applied. For example, if that force is tensile force, that means there is certain specimen and we are pulling it. This is tensile load. We already discussed in types of loads. When that is the case, pulling action is there, then it elongates, its length increases by some amount. So this will be L dash and this will be L. Change in the length delta L is equal to L dash minus L. This change in length divided by original length will give us strain. That is strain. So now you might have got the preliminary understanding of what is stress and what is strain. Now what I need to, or what I want to say from that is, different materials have different properties or different mechanical strengths and properties. Accordingly they will resist the applied load. The capacity of resisting, we can increase the applied load to certain extent. Say we are increasing, this is the applied load Fa, we are increasing it and going on increasing at certain limit, this point, fracture limit, the material will break away. This will break away, this part will become separate and this part will become separate, break away. That break away, that force which is required to break this specimen will be different for different materials. So that means resisting force developed, maximum resisting force Fr max, is different for different materials depending. Why? Because every material we know is made up of certain layers or grains which are oriented in certain fashion or directions. Depending on the orientations, their mechanical properties vary and the strengths vary. As the strengths vary, maximum resisting force develops vary. That's is depend based on that. Also another is some materials will elongate more and some materials will elongate less. That means change in their dimension will be more for some materials, will be less for some other materials. So these properties change. Accordingly, there will be different stress strain diagrams. So for applied load, there will be resisting force, accordingly resisting area. Every time we change the load, certain area is changed, accordingly we will get certain stress, and also correspondingly we will get some strain. When we plot this sigma and this epsilon, that means stress and strain, we will get stress strain graph. So the tests for like tensile tests are conducted for different or varied materials, of which profoundly used one is mild steel. The tensile test on a mild steel specimen are the one which is plotted and explained in most of the textbooks, and is very important because for this material each point A, B, B dash, C, D, these points are clearly exhibited. For other materials, curve, the stress strain curve is not so clear. So we will study those things in later part, but for this part I will explain you what is this A, what is this B, B dash, C, D and E, etc., and what is this zones, etc. It is anyway, if you have already covered this subject, it is just a recapitulation for you. If you are new to this subject, then you must go through what I am trying to tell you. There, observe one thing here. This is the solid curve, which we generally treat as stress strain curve for mild steel, and this curve is actually called as engineering stress strain curve. This is not the true one. There is true stress strain curve which deviates from certain point considerably. It does. What is this? I will tell you just now. Initially, we have to understand it is a result of a tensile test in which we apply a tensile load on a given mild steel specimen. Say for example, this is the initial specimen. Now we are applying tensile load, say F1. With F1 load is we are applying accordingly certain. So in tensile case, since we are applying the load normal to the area of cross section, stress generated here across any cross section, since it is a uniform cross section, across any cross section, sigma will be, say since it is the first case, initial case, let it be sigma 1 will be F1 and initial area of cross section be A1. Now in the case 2, we will increase F1 by, say for example 10 newtons or 100 newtons or 200, whatever it is, or 10 kg in terms of weight depending on the machine. Say for example we are increasing it by some, say for example 15 newtons. I am doing this only to signify you about the concept. It doesn't mean that we only increase by 10 or 20, we may increase by 15, 16 as well. So it depends case to case and person to person basis who is experimenting in actual. To signify you about the concept, I am telling you this. Now this is a given volume of the cylinder. Cylinder is pi r square L, where r is radius and L is length of the specimen. Volume is fixed. This volume or this piece only gets elongated, but elongated means length is increasing. When length is increasing, for the overall entity to remain constant, then this r must vary. That means this area of cross section of the base should decrease in proportion to the length, increment in the length, so that overall value remains constant. What I mean to say is, initially for suppose area is set in say 5 into length is 3. When this 3 is increased into 5, automatically proportionally 5 should decrease to 3, so that overall value 3 into 5 or 5 into 3 remains the same. That is overall volume is 15. That is an example. Now when tension is applied, there is certain elongation. Say this is case 2, stage 2. I mean, as F1 is increasing, getting increased at F1, this is the position. When we increase F1 to certain, increase it to F2 further, it is bit elongated.
then case 2 will be sigma 2 equal to, in case 2 stress will be F2 or F2. What is F2? Say F2 equal to, what is F2? F2 equals to F1 plus say some 100 newtons. So F1 plus 100 divided by A2. A to C, from here to here area reduces. Further when we go, it further reduces area and elongation happens. As length increases, area of cross section decreases. So when load is increased to F3, this is the case. So it goes on till an ultimate point E, where necking happens. At point D, once the stress is reached at point D, this is ultimate stress point. When that is reached, then what happens is area will reduce so much and small necking starts. Necking phenomena starts. Say this is some step 5, F5. Once this situation comes, once D point is reached, in the necking zone when we enter necking zone, instead of requirement to increase F5 to F6 with the decrease itself, even if we try to reduce very quickly before even we are trying to decrease the force values, it starts breaking by cup and cone fracture, because mild steel is a ductile material and ductile materials under tension fail by cup and cone fracture. What I mean to say, when you zoom this part, how this here I am drawing, it will come like this, something like this. So this is like conical shape, this is some cup shape. So this will be the fracture that is visualized after the specimen is broken. So this happens, this breaking, ultimate breaking happens at E. From this to this, that means this D to E takes very less time. Once this reached means we have crossed the entire limit and the specimen is ready to break. So now we are not going up to that point. Now let us focus here. Now this is F3, here length is further increased. Let F3 be F2 plus 100, that means F1 plus 200. F1 plus 100, again plus one more 100, that means F1 plus 200. Then sigma 3 will be F1 plus 300 divided by 200 divided by A3, third case. Now observe, for sigma formula is F by AR. This FR anyway we are increasing, F1 again plus 100 so on. That's why this value anyway it will increase, sigma value, stress value anyway it will increase. But further when this AR is getting reduced from stage to stage, it is obvious, it is reducing, we are able to see. When it is reducing, this denominator in a fraction, when it reduces, overall value increases further. That means sigma values are high, very high. So that is the true case, actual case. What is happening, that if we plot those things and corresponding strains, this is what we will get, true stress strain curve. But every time measuring this is difficult, and so that is one point. Another point is, that is not required, it's true, we do not require true stress strain curve for our study in strength of materials. I will explain why this second point. Anyway, first point, it is obvious for you, it is easy to understand. Every time taking out the specimen and checking the area of cross section, it is very time taking and very hard. So at every point we cannot check area of cross section. So that is the first point, is obvious. Second point is, we neglect true stress strain curve and we consider only engineering stress strain curve. Why it is, I will tell you just shortly. Now engineering stress strain curve, how we obtain is, we, like in true stress strain curve, in engineering stress strain curve also we change the values of F1, we go on increasing whatever actual value of F1, F2, F3 we are taking, those values we put. But for area of cross section we do not change, whatever value here it is there, same area of cross section we maintain throughout our calculations. So when area of cross section is made constant, observe initially it is high, area of cross section is more, in later studies it is less. In spite of that, we are maintaining the same cross sections, means we are maintaining a higher value. When denominator is maintained higher value, automatically overall value will be, increment in the overall value will be low or slow. That's why in true stress strain it is increasing, stress is increasing very quickly, fast. But in engineering stress strain curve, since we are lagging behind due to use of original area, which is higher in every case compared to others, in denominator we are using it, so overall value of the fraction will be bit lower when compared to the true values. So that is the differentiation here we have to understand. In engineering stress strain curve, we only use initial area of cross section. We don't make the area of cross section calculations dynamic, it is static. That means we only use one value, that is the initial value. Now the point to understand is, why do we only consider engineering stress strain curve for our strength of material subject? I already told you that in engineering strength of material subject, we consider our study only up to elastic zone. What is elastic zone? We will come to know shortly in the definitions. It is that point below which if you load the material, we apply the stress and again we unload it, remove the stress, that is remove the load, the object will deform and again come back to its original zero state, original dimension, whether it is distortion or whether it is distortion or deformation, whatever it is, it again comes back to its original place if the loading, unloading, everything is always below the elastic limit. And before this, before elastic limit, the change in dimension, this delta L, is very less, of the order of 0.1 mm or even below it, less than that. When dimension is 1 meter, that means 1000 meters, compared to 1000 meters, this 0.1 meter is very 0.1 mm, sorry, not even meters. Compared to 1000 mm or 2000, 3000 mm, each component is that much lengthy. Compared to the value of 1000, this 0.1 is negligible. Okay, so accordingly, when that is there, then change in the area will be very negligible. And when the change in area is very negligible, then whether you use original area time to time or the initial value of the area, the overall result of sigma will be almost same. So that is the reason why from here to here there is no deviation or difference between true stress strain curve and engineering stress strain curve. They are almost merging. If you zoom, there it, of course, true stress strain will be bit apart from the and a bit above the original engineering strain curve, but the difference between true stress and engineering stress can be eliminated or neglected because it's very negligible, very small. That's why, since our studies are up to here and up to here, true stress and engineering stress are almost the same with a negligible difference between them. That is why we generally consider engineering stress strain curves or engineering stresses for our discussions, because it is useless to consider 0.001 or 0.01 change in the area for stress calculations. If it is considerable change happens only after yield strength, yield point is crossed. After that only we need to consider true stress strain behavior. That is another part. Now elastic zone I have told you. Up in that elastic zone up to point A, increase in stress makes or creates an proportional increase in strain. That is, a linear relationship is there between stress and strain up to this point A. That means up to point A, this is a linear zone, and linear zone means it follows Hooke's law. What is Hooke's law? We will study later shortly. After that, up to here, of course, this everything is a subset of elastic zone. In that, here it is a non-linear relation between stress and strain. Once this point B, upper yield point, is reached, then there happens a plastic flow of material. When there is plastic flow of material, then once you cross this point, load the material beyond this point, even if you unload, there will be a small recovery of the deformation to original shape, but completely there will not be recovery to original shape. There will be small permanent set. We will discuss in the later slide. So this from here to here, it is a yield area or yield zone, where it is called as plastic zone, where is a plastic flow of material happens with a permanent set. Up to certain point C, the flow of plastic flow is very smooth, and that's why material yields very easily with the same stress, but straining goes on increasing. That means deformation goes on happening with the same stress, almost the same stress, up to the point C. Once point C is reached, there always we know that material is formed of grains or layers, and these layers or grains throughout the material are not the same. Up to some extent it will be same. After that it may change their orientation. When orientations change, the change where the direction of grains orientation of everything is changing, that change will act as or inhibit the flow, plastic flow. Due to that, we need to increase our stresses to further create strain. So that's why what is happening, recrystallization or reorientation of grains are required, which require high application of stresses to create any further strain. That's why it is strain hardening zone. Once maximum strength of the material is reached, after that you need not create or you need not apply any further stress. Automatically necking will happen and it will break very, very soon. So these are the zones: strain hardening, necking, plastic and elastic zones. Now one thing we need to discuss after this: elasticity. In elastic zone, what it was, property by virtue of which a material deformed under the applied load is enabled to return to its original dimensions when the load is removed. That's what I was telling. Plasticity, anyway, property by virtue of which the material undergoes inelastic strain when loaded beyond elastic limit. So this plasticity we will discuss only when yield point is crossed. Beyond elastic limit means yield point has to be crossed. So that plasticity we will not read here in strength of materials. But one thing you need to consider is, in manufacturing operations such as pressing, forging, this has a major application in automobile industries. You might be knowing, if you have studied the course basic manufacturing or workshop technology. In that course you will study what is pressing, what is forging, those operations. In those manufacturing operations, we need to make or transform a given block of material into the final product shape using some die by hammering or pressing. That can be done irreversibly only when material is plastically flowing. That is what plasticity is. Everything you need not go into depth and details, that is advanced subject, or you can get that in subjects like material science concepts. Further, when we go these things what I was telling, within elastic zone, say if this is elastic limit, before this only if you load and unload, even if you load and unload n number of times, every time when you unload, material will get back to its own original shape. But if you cross and stress the material above its elastic limit, it will try to regain the shape, but it will fail to reach its original state. There will always be certain permanent set. That means epsilon strain will not be equal to 0. Final strain will be there. Some point value will be there. This part is called permanent set. So when this happens, when loading is loading is done above the elastic limit. So with this we conclude this class. We will continue in lecture 1.4 with further concepts. Thank you.